All right, so this is section 4.5. This is the last section in chapter 4. It's called the substitution rule. This rule is the first new antiderivative technique that we're going to learn. So far, we know how to do the basic power rule antiderivatives. This antiderivative technique will undo the chain rule. So basically, it's going to undo a composite function. It's going to give us a way to take an antiderivative of something that was a composite function from its derivative. So in order to understand that, let's kind of review the fact that if we took a derivative of a composite function, 2x cubed plus 3x, the whole thing to the fourth power, it would be a chain rule. So the derivative of that, you would bring the 4 out to the front, times 2x cubed plus 3x, reduce the power by 1, and then multiply that by the derivative of the inside, or the composited piece, which is going to be 6x squared plus 3. So there's the derivative of your composite function. Well, then it stands to reason that if I was to take the integral of the derivative that I just found, so if I'm going to take the integral of 4 times 2x cubed plus 3x to the third power, times 6x squared plus 3, if I'm going to take that integral, I would get back to the original function that I took the derivative of. However, because I don't know if I was, in this case I do know, but if I didn't know that, I would have to add a plus c, because I'd have to have any possible constant added onto my original function that I could take the derivative of and still get to that. So again, hopefully that makes sense. If you took the derivative of this function and got the 4 with the the 2 parentheses on the right, then if I took the integral of that, I'm going to get back to the original function plus some value c. So, excuse me, the chain rule in general says if I was to take the derivative of f of g of x, it would have been f prime of g of x, so the derivative of the outside piece, times g prime of x, the derivative of the composited piece. Therefore, the integral of f prime of g of x times g prime of x dx should get us back to the original f of g of x, again, plus some constant c. Okay, hopefully that makes sense. All right, so question is, how do we do this? If we don't already know the original function, how do we actually get back to it? So that's what I'm going to teach you now, and it's called the substitution method. So in our example, I'm going to substitute a variable u in for x to the fourth plus 2. So my u is going to be x to the fourth plus 2. And then I'm going to take the derivative of both sides of that equation, both sides of this equation with respect to x. So the derivative of u with respect to x is du over dx. The derivative of the right side with respect to x is 4x cubed. And then if I was to solve this equation right here for du, I'm simply going to multiply the dx over to the right-hand side and get 4x cubed dx. Now I'm actually going to add another step onto here, which says that if I was now to solve this equation for dx, I'm going to divide both sides by 4x cubed. So then I would get that dx equals du over 4x cubed. Why would I do all of this? Why am I trying to do this? Well, I'm trying to make this integral easier to do, because looking at it right now, you've got some kind of a product with a chain and all kinds of stuff going on. It does not look easy to do. Well, that's what I've been doing with all this extra work over here for, is to make it easier. So now I'm going to rewrite my integral. I'm going to make a substitution. Whenever I see x to the fourth plus 2, I'm going to plug in u. So x cubed, that doesn't change. Cosine of, well, here we go, x to the fourth plus 2, that now becomes u dx. The problem is I've still got this x cubed and that dx right there. I can't take an integral unless it's all down into one variable. So in order for me to do that, I have to find a way to get rid of those. Well, the other main thing is this is now in terms of u, so this also needs to be in terms of u. So I need to get rid of that dx. That's why I did this step. So now I have a way to get rid of dx. I can substitute du over 4x cubed in there. So I'm going to have the integral of x cubed cosine of u times the new dx, which is du over 4x cubed. And wouldn't you know it, through a little bit of algebra, the x cubes will cancel out. Now all I have left are terms of u. I do have a constant with that 4 in the denominator, but we should know from properties of integrals that we can pull a constant out to the front. Now the 4 is in the denominator. It needs to stay in the denominator, so really I'm going to pull a 1/4 out to the front. Then I'm going to have the integral of cosine of u du. That is something I can do because I can take the antiderivative of cosine of u, which is sine of u. So I'm going to get 1/4 sine of u. Don't forget the plus c. Now, we did not start off in terms of u. We only used the u to make this an easier integral to do. So now we're going to go back and we're going to plug the original u value back in for u because we started off in terms of x, so that's what we want to finish it as. So it's 1/4 sine of x squared plus 2 plus c. That is the integral of x cubed cosine of x to the 4th plus 2 dx. This is most commonly called U-substitution because typically we let u be our substitution variable. It doesn't have to be, it just needs to be something different than the variable that's given to us. So you could use t's, you could use p's, you could use just about anything else you want to. We will most commonly use u. So one question might be, well, how did I know to let that part right there be the u value? And that would be a good question to ask. Remember, what we are doing is we are undoing a chain rule, which is a composite function. So what you want to do is you want to look for the most composited piece. And I say the most composited piece because there can be multiple composited pieces. You want to look for that first. That's typically going to be your u value. Not always, but typically. And as we run through these, you're going to see some examples of other things where it might not necessarily be, but for the most part it will be. So it's the thing which is the most composited piece. X cubed is not really composited. Cosine is not really composited, but the angle of cosine is the composited piece. A lot of times look for a parentheses or a grouping symbol. That helps. Okay. In our second example, it's the integral of the square root of 2x plus 1 dx. Okay. You can't use a power rule antiderivative here because the 2x plus 1 is all within the grouping symbol of the square root. So you couldn't just change the whole thing to a 1/2 power and do it that way. So we're going to get rid of the hard part here, and we're going to let u be the composited piece. So u is going to be 2x plus 1. I know I'm going to need to get rid of the dx. So in order to do that, I'm going to take the derivative of this function with respect to x. So du over dx is simply going to be 2. And then I'm going to solve that equation for dx. So the first thing is we multiply both sides by dx, and then we're going to solve for dx, dividing both sides by 2. So you get that dx is du over 2. And now we can make our substitutions. So I'm now going to have the integral of the square root of the 2x plus 1 becomes u. The dx part we replace with our du over 2. Okay, I'm going to rewrite it just to make it a little easier to take the antiderivative. I'll pull that 1/2 out to the front because it's a constant. And I'm going to change the square root of u to the 1/2 because that is something I can take an antiderivative of. So then we'll get 1/2. U to the 1/2 antiderivative is u to the 3/2 Dividing by 3/2 is multiplying by 2/3, so I'll put a 2/3 out in front. And don't forget, plus c. Now we can simplify the 1/2 times 2/3, because that's going to give us 1/3. And we'll replace the u with the original u value of 2x plus 1, because we need to put it back into its original variable. And that is your antiderivative. All right. Number 3. By the way, there's just lots and lots of examples in here, so we're going to go through all of those. Number 3. So it should be pretty obvious that the composited piece here is the 1 minus 4x squared. But I also want to tell you that a denominator itself is also composited. Okay, I'm going to erase this, but I just want to show you what I mean real quick. If all I had was, I don't know, x, whoops, did not mean to use that. If all I had was x plus 1 over x minus 2, you might ask yourself, well, I don't see anything which is composited. The denominator is technically composited because if I put these things in parentheses, I could rewrite this as x plus 1 times x minus 2 to the negative 1 power. You can see how this, being raised to the negative 1 power, is technically more composited than the x plus 1. It's definitely within a parenthesis. So that's what I mean by the most composited piece. And a denominator is a composited piece. So in this case, we're going to actually let it be the inside of the denominator square root. So u will be 1 minus 4x squared. Then the derivative of that is going to give us negative 8x. Solving for the dx, we multiply dx to both sides, and then divide by the negative 8x to actually get dx. So that's going to be du over negative 8x. Okay, let's do our substitution. So I haven't done anything with that x. We know it's got to go away, though, otherwise this isn't going to work. And then we'll have the square root of u, because the u is 1 minus 4x squared, times our new dx, which will put everything in terms of du, so it's du over negative 8x. And again, the nice thing is that x cancels out that x. I can bring the negative 1/8 out to the front, which would leave me with 1 over the square root of u du. And now what I need to do is I need to change that. 1 over the square root of u. Square root of u is u to the 1/2, but since it's 1 over, I'll bring it up. It'll be u to the negative 1/2 power. And now I can take an antiderivative. So we get negative 1/8. Adding 1 to negative 1/2 gives me a positive 1/2. And dividing by a half is multiplying by 2. Oops, that should not look like a minus. Plus c. So let's see, negative 1/8 times 2 is negative 2/8, or negative 1/4. And we have to replace the u with the original 1 minus 4x squared. So that becomes the square root of 1 minus 4x squared. You could have left it as 1 minus 4x squared to the 1/2 power. It doesn't matter. Just know that they are the same thing. And there's your antiderivative, your integral. Okay? Number 4. Once again, this is just the integral of cosine of 5x. The only composited piece is the angle itself, 5x. So that has to be our u value. The derivative of 5x is just 5, multiplying the dx over, and then dividing by the 5 to solve for dx is going to give us du over 5. So then rewriting the integral, it becomes cosine of u times the new dx, which is du over 5. I can pull the 1/5 out to the front, and I am left with the integral of the cosine of u du. So now I can take the antiderivative of cosine, which is sine. So we get 1/5 sine of u plus c. And then I can go ahead and replace the u with the original x values, which was 5x plus c. Now there is actually a shortcut to this one, which we will eventually talk about. But for right now, that's the process that you would use. Okay, hopefully that makes sense. Let's move on. All right, number 5 is a bit tricky. The composited piece still is 1 plus x squared. That's under the square root. That's what we're going to let our u value be. And then we'll take the derivative and we get 2x. And then multiplying both sides by dx gives us 2x dx. And then dividing by the 2x dx is going to be du over 2x. All right, so let's go ahead and make our substitutions and we'll see why we have a problem. So we're going to get the square root of u times x to the 5th times our new dx, which is du over 2x. And hopefully you can see where the problem's going to come in now. I can bring the 1/2 to the front, still got a square root of u, but unfortunately, that x is only going to get rid of one of those and make it an x to the 4th. That's going to create a problem, because I couldn't algebraically get rid of that x to the 4th. There is a way to do this still. A bit messy, but we'll be able to figure it out. So what I can do is I can go back to my original u values right here. And I can say, okay, what if I was to subtract 1 on the both sides of that equation? So then I would get that u minus 1 is x squared. Not looking for x squared, though, I'm looking for x to the 4th. Well, what if I were to take and square, whoops, that's supposed to be green, and square this? Well, if I square the right side, that means I have to square the left side. X squared squared is x to the 4th. So x to the 4th is the same thing as u minus 1 squared. Now everything will be in terms of u. So I'm going to replace my x to the 4th with u minus 1 squared. You might say, well, wait a minute, that doesn't really help. It does actually, because I'm going to bring this stuff over to the left because this one gets a little bit lengthy. I can rewrite u, square root of u, as u to the 1/2. And I can FOIL the u minus 1, which will give me u squared minus 2u plus 1 du. And then I can distribute the u to the 1/2 into every term. So again, I'm going to have 1/2 integral. Now u to the 1/2 times u to the 2, we add the exponents together. We get u to the 2.5, or u to the 5/2 power, minus 2 times u to the 1/2. Well, that's u to the 1/2 times u to the 1. So 1 plus 1/2 is 3/2. And then u to the 1/2 times 1 is just u to the 1/2. Now, even though everything has a fractional exponent, I can take antiderivatives. So 1/2. Now the integral of u to the 5/2 will be u to the 7/2. Dividing by 7/2 is multiplying by 2/7. Okay, let's repeat that process. Minus u to the 3/2 will become u to the 5/2. Dividing by 5/2 is multiplying by 2/5. Oops, forgot my 2. So then times 2/5. And then the last one, u to the 1/2 becomes u to the 3/2. Dividing by 3/2 is multiplying by 2/3 plus c. Last step, we didn't start off with u, we started off in terms of x, so we can simplify. So I am going to distribute the 1/2 to everything, and I'm going to replace the u's. So 1/2 times 2/7 is 1/7. Replacing the u with 1 plus x squared, now to the 7/2 power, minus 1/2 times this 2 becomes 1, so that leaves me with a 2/5. Again, replace the u with 1 plus x squared to the 5/2 power, See if I can fit all this in there. Distributing the 1/2 to the 2/3 will give me 1/3. Replace the u with 1 plus x squared to the 3/2 power. And don't forget plus c. A bit longer of a problem, definitely more algebraic, but not impossible to do. All right. I think this is probably a good place to stop, because if you recognize something in number 6 that we haven't dealt with yet, it is bounds. So we're going to stop and we'll come back with a second video. There may be 3 videos overall in this one, haven't decided yet.